Starting off our second video, we will begin with dipole, or dip. Now for this one, we're looking at the attractive, or attraction, from molecules with charged ends. I'll put right here. And I'll explain that more in just a moment. The more polarity, the more attraction. And just as a reference, if you look in your book on page 431, you'll see a pretty good depiction of this. I'm not going to pull that out because I had some of it in the PowerPoint. I just really don't want to do it right here. So the idea is it's not that there's a positive, negative, like a sodium or a chloride ion. This is in a molecule, so think like sugar. The different atoms in the sugar molecule will have different charges. So for example, the oxygen is going to have a relatively negative charge comparatively because it's very electronegative. It attracts electron density towards it because of greater Zeph, right? And then other atoms like hydrogen, if they are anywhere in the proximity in this structure, they're going to have a relatively positive charge. So when you have a molecule that has, hydrogens or oxygens or some other groups of atoms that have negatives versus positives, there's going to be attractions for one molecule. So think of one molecule with a positive side on it in comparison to another molecule with a negative side on it. You're going to have this different attractions in there that the two different molecules will be pulled towards each other. So that is called dipole. Okay. Let's look at the last one in this example, which is sort of like dipole. And we call this one specifically hydrogen bonding. And people get this one a little bit confused. We'll see how we can do with this. It is bonding between a hydrogen, very specifically, which it itself is bonded to, and it must be one of these three: nitrogen, oxygen, or fluorine. And an electron pair on another, that's not another, another atom, and it's usually nitrogen, oxygen, or fluorine. So this is kind of the classic example of this one is to use water. And of course, we've got these electron pairs on the oxygen. And then I'll do another water, but I'll do it upside down here. So to tell the difference, to distinguish between these different types of bonds. Let me get this little zap here. Put this back in focus a little better. Anyways, this is an intramolecular force. So it holds the hydrogen to the oxygen here. And as far as a charge, net charge, the oxygen is relatively negative and the hydrogen is relatively positive, just like we were kind of talking about in dipole. But this is very specific, that we actually are talking about oxygen and hydrogen. They are bonded together. As we said, in order to have a hydrogen bond, this hydrogen must be must be exactly connected to the oxygen. And because of this, the electron density of this pair, there's a pair of electrons here, right, in the bond, it is pulled more closely to the oxygen, making this relatively negative, and this is relatively positive. Now, because of that, positive, negative electron pair, there is a intermolecular attraction between these guys. So this bond, or excuse me, this pair of electrons is attracted to this hydrogen. I don't know why I put it to the charge. And then you have an attraction between these guys. So it's a very strong attraction between this hydrogen and a lone pair of electrons, and the same thing up here. These are very specifically called hydrogen bonds. Now, the hydrogen could also be doing this with nitrogen or fluorine in a different atom molecule. But it has to be, the hydrogen must be attached to one of these guys through a chemical bond, an intra, and then you have this intermolecular force with these guys. You have to work on that one a little bit. I know it can be confusing. All right, let's do our next one here. Let's go on to ion dipole. And ion dipole is to think of like a sodium ion in a water solution. So water has dipole, and an ion is charged. So we'll write this one down. It is the attraction between an ion and a polar molecule, like water. And this is responsible for some substances being more soluble than others. I'll just leave it alone at that. Typically, we're talking about water when you're talking about solubilities, how soluble something is water. So, for example, you put one substance in water, call it sugar, and how well does it dissolve? I put the exact same amount in there, like 5 grams of sugar in water. And does it dissolve or not? I can do the same thing with salt. Does it dissolve or not? Now, sugar doesn't have ions, right? Doesn't form ions, does not dissociate in that matter. Whereas salt does, it forms positives and negatives. It forms sodiums and chlorides within water. They separate out. And the reason they separate out is because there's an attraction between the water and the ions. So it solvates those ions and they are separated from each other, the sodium and the chloride, and they become attracted to the water molecules. So that's an ion dipole attraction. Okay, let's bounce over and do a couple homework problems in your homework packet. So we will start off with number 6. The molecules propanol and ethyl methyl ether have the same molecular formula. So they have all the same stuff in their formula. But they have different normal boiling points. Let's rationalize differences. So I'm not going to ask you to know what those things are, but we'll just go ahead and put them together. The first one I'll draw here is the ethyl methyl ether, this guy here. So an ether is something that has an oxygen in the middle. You don't have to know this. And it has an ethyl on one side and a methyl on the other. So here we go. There is the methyl group on the ether. And here is the ethyl group on the ether. So this is an organic group. And again, we don't need to know this. Ethyl methyl ether. Propanol is like propane, 3 carbons. And the fact they're calling it propanol with an O means it has an alcohol group, and there it is. And if you're doing your accounting here as far as stuff goes, these have the exact same carbons, oxygens, and hydrogens based on the formula right here. But they have different normal boiling points, and we have to rationalize it based on some of the things that we've been talking about here. Don't forget this has lone pairs of electrons hanging out here. And we're saying they have different boiling points, which means they have different attractions to stuff. And based upon the things we were talking about in the previous lectures and up to this point, we have to kind of rationalize, say, okay, which one would have a higher boiling point? So which one has more attraction for like molecules? And it's like, well, is it this one that has this oxygen hanging out here? Or is it this one that has this oxygen hanging out here? And there's a little bit more going on here than that. I'll give you a clue. Not much of a clue. It's this one. And the reason it is because this has the exposed hydrogen thing going on here. And it can have hydrogen bonding. So because of this oxygen to hydrogen bond in here, you have a positive relative nature here. So if I have another propanol molecule hanging around, I can have a hydrogen bond between this hydrogen and the oxygen group here with the lone pairs of electrons. So that's going to form a potential hydrogen bond with itself. And that's a strong attraction. This one here can have dipole-dipole because of hydrogens and an oxygen having an attraction there. But it's not hydrogen bonding because of the very specific conditions we talked about just a few minutes ago. It can form dipole-dipole, but it cannot form hydrogen bonding because you have to have the hydrogen directly connected to the oxygen in intra-molecular force. So I'll just write that down really quick and we'll finish this lecture up. The OH in the alcohol is more exposed and can form, I'm going to say HB for hydrogen bond. All right, that's the end of this lecture.